All right, everyone, taking a peek at a question from our homework last night, which was our navigation or our relative motion worksheet. Taking a look at number 5 on that worksheet. It says the captain of a ship aims his ship with a velocity of 25 meters per second directly north across a river whose current flows at 8 meters per second to the east. The river is 850 meters wide, and then we got to find some things. Okay, let's not worry about what we got to find right now. Let's worry about what we have right now. We aim his ship at a velocity of 25 meters per second. This is a solid line vector, dotted line vector problem, right? What do we have there? A solid or a dotted line vector? In other words, does that contribute to where the ship goes, or is that where the ship actually goes at 25 meters per second? He aims in a certain direction. Does he end up there, or is that just contributing to where he's going, Jared? Good, good. Contributing to where he goes, which means it's a solid or dotted line vector. Nathan? Good, it's a solid line vector. So let's draw that directly north, 25 meters per second, as a solid line vector. Does that make sense, guys? All right, our next vector that we're given here is a river current of 8 meters per second to the east. Does the river current contribute to where the ship ends up going, or is the river current where the ship actually goes? Luca, does it contribute, or is it where the ship actually goes? It contributes, good. So that's going to be a solid line vector as well. Now we got two solid line vectors. We're going to draw them front to back. So let's draw our 8.0 meters per second over this way. Now, some of you are looking at this 850 meters, the width of the river, saying, how do I draw that into my vector diagram? Well, you can't mix and match velocity with displacement. You can't. You can't do that in one vector diagram. It's got to be two separate diagrams. So let's just, over here, let's draw a river in here. And then over here, just label the width of the river 850 meters. Not as part of our vector diagram, but just somewhere so that we know how wide the river is. What are we looking for here? The velocity of the ship relative to the shore. We're looking for the dotted line vector, right? Where the ship actually goes, right here. So how fast the ship is moving relative to the shore. Now, we're looking for the resultant vector there, at least the magnitude of it, and the direction. So let's get R there now. 25 squared plus 8 squared. What does it give me? Yep. 26 meters per second. Good. And theta is the inverse tan function of opposite over adjacent. What's the opposite side for this one? What's the opposite side for this one? Jordan? The opposite side is not 25. The opposite side, remember, is the only side of the triangle that's not touching the angle. Got that? Now, there's two sides touching the angle. That's the resultant of 26 and this side of 25. The only side not touching the angle is 8 meters per second, yeah. Good, so that's opposite, and adjacent is therefore going to be 25. Does anybody have what that angle works out to be? Yep, 18 degrees, thank you. Now, how do we express that? 18 degrees, what of what? We have north-south axis, we have east-west axis here. This angle that you see here, theta, 18 degrees, is only touching one of the axes. It's only touching north or east. Which axis is it touching, the north or the east? North. So that means it's measured from the north. It's measured from the only axis it's touching. It's measured from the north. That means it's going to be 18 degrees east from the north, or 18 degrees east of north. Right? Is that good, guys? Where did that 850 come into play here? It didn't. Don't worry about that. Sometimes we get numbers that don't matter. Right? That 850 is going to matter later on in this question, but so far it hasn't. If you only had question A and you were given the information you were given, the 850 would be irrelevant. Okay, the time that it takes the ship to cross the river. This is a good question. I like this. Mathematically, it's a cinch, mathematically. But conceptually, it's a little bit tougher. We're going to use the equation v equals d over t to solve this. Velocity is displacement over time. The ship is moving at a constant velocity across there at 26 meters per second, right? 26 point whatever it was, meters per second. We want to rearrange this to solve for time. It becomes delta D over V. Here's what just about everybody wants to do for this question. They see a displacement. Oh, 850. That's where that comes in, right? 850. Divide it by the velocity. What do we just find the velocity to be? 26, right? But that's wrong. That's wrong. Just because we just solve for that velocity doesn't mean that's the velocity that we want. Bree, what were you going to say there? No. I thought you were interrupting me because you had something to say. No? Okay. What's wrong with this? Yep. Yeah, you think of it in two ways, yeah, and that works. If you're going to use the velocity this way, right, 26 meters per second at 18 degrees east of north, then you need the displacement that the ship traveled this way. We don't have that. It's not 850. You could, if you wanted to, okay, say, well, this is 850. We have the angle there. We could find the resultant displacement, and you could use whatever that displacement is over 26. That would be fine. But the easier way to do this is to say 850 over 25. Why 25? Because if you're using a displacement on the y-axis, the velocity must also be on the y-axis. If you're using the velocity at the angle of 18 degrees, then the displacement must be at 18 degrees. If you're using the velocity horizontal, x component, then the displacement must be x component. The bottom line is, whenever you're using that equation v equals delta d over delta t, it doesn't matter which velocity you use, but you've got to be consistent. If we're using a displacement on the y-axis, like we are here, then we have to use a velocity on the y-axis as well. The 25 goes with the 850. This displacement, whatever that is, would go with the 26. And this displacement, whatever that is, would go with the 8. Does that make sense? Give you a simple thing to illustrate this, okay? You're traveling down the road at 10 meters per second. Got this? 10 meters per second to the east for a time of 2 seconds. What's your displacement? What's your displacement, Sam? 20 meters? That's your distance traveled. What's your displacement? 20 meters to the east. Notice the velocity and the displacement were in the same direction. If they're in the same direction here, then they got to be in the same direction in this question as well. You can't have a velocity to the east and a displacement to the west. You can't have a velocity at 16 degrees and a displacement that's straight across the river. Okay? Doesn't matter which one you use, but be consistent through that problem. Does that make sense? Does that make sense, guys? That's kind of a tricky thing to wrap your mind around sometimes. But. Okay, so when we do that math, I think it works out to be 34 seconds. Is that right? How far downstream does the ship end when it reaches the other side? We're going to use v is equal to delta d over delta t for that one as well. But this time we're going to rearrange it to solve for delta d. How far downstream does it end? V times t. What velocity do we use? If we want to find out how far downstream this way to the east it goes, what velocity do we need to use? Victoria, is your hand kind of going up there, or just kind of stretching your fingers or fidgeting? Sam? No. If we want to find out how far east it goes, then what velocity do we need? 8. The velocity to the east, right? Okay, if we use the 26 meters per second, okay, that's fine. But understand, when you get the displacement there, you're not going to get the displacement to the east. You're going to get the displacement at 18 degrees or whatever that was. the displacement in the same direction as the velocity. If we want the displacement to the east, then we need to use the velocity to the east. Now, what time do we use? 34 seconds, right? Takes 34 seconds to get across. What does that work out to be? 30 times 8 is 240. 4 times 8 is 24. 364. Is that right? No, 344. Anybody? 364? Or 272? Sounds good. Is it 272?
I think so.
Oh, yeah. 30 times 8 is 240 plus, all right, whatever. 272 meters, which really should be 2 digits, right? 2.7 times 10 to the 2 meters downstream. So we're looking for the displacement to the east. Let's use the velocity to the east. Now, here's a quick question for you. Might not be quite so simple, though. Why did I have to make sure that I use velocity east, displacement east, velocity north, displacement north? Why did I have to be so consistent with velocity and displacement? But time, I can just put time wherever I wanted, east or north or whatever the case may be, Peyton. Good. Time's a scalar. So it's not an east or a north kind of thing like velocity and displacement are. Does that make sense? All right. Let's do another example here. So it's a little bit different. This one says, the pilot of an airplane wants to go directly north, at a velocity of 500 kilometers per hour, but there's a wind blowing to the east. We want to know where the pilot's got to aim in order to accomplish this. This is like the example that I was telling you about the other day, right? We're driving our car towards Calgary. It's really, really windy. There's a wind blowing from the west toward the east. So much so that you're kind of steering towards the mountains so that you stay going straight north on the road, right? Where do you have to aim in order to end up going north? Intuitively, when we're driving a car, we just do it, right? We respond, 1,000 times a second. Our brains respond to the external stimuli, and we steer in the right direction, right? We aim in the right direction. But if we had to figure that out, if we had to calculate that, if we couldn't see where we were going, how would we figure out exactly where to aim? The pilot wants to go directly north. Is that a solid line vector or a dotted line vector? This is probably the hardest one yet we've had. Solid or dotted line, Jeremy? It's a dotted line, yeah. It doesn't say the pilot is actually going north, but if the pilot wants to go north, we'll assume that he or she actually goes north. So we're going to make that a dotted line. That's not contributing to where we go. That is where we go. So dotted line, 500 kilometers to the north, 500 kilometers per hour, I should say, to the north. Now, there's a wind blowing to the east at 85 kilometers per hour, solid or dotted. Wind, does that contribute to where I go, or is that where I go? Solid. Listen, guys, if we already established that I'm going north, well, then I'm not going east. If I'm going at 500 kilometers per hour to the north, then the 85 must be contributing to where I go. Now, here's the question. Here's the tough part of this one. Where do I draw that? I've got 4 possible positions here to draw that 85 kilometer per hour vector. 2 of them are correct. 2 of them are not. Does anybody want to take a stab at one position that I can draw that vector in? Position 1, 2, 3, or 4? Where's one place that I'm allowed to draw that, Sam? Position 1? Okay, let's erase the rest of them then, and let's just check that. Remember, my resultant vector is my dotted line vector, right? It has to be drawn from start to finish. Can I draw that dotted line from start to finish when I have that drawn like that? No, that's drawn from finish to something else, right? Maybe I could draw this. Finish to start doesn't work. So position 1 doesn't work for us, right? That makes sense? That resultant vector has to be drawn so that the back of the vector is against the back of the vector, and the front of the vector is against the front of the other vector. Back to back and front to front. Position 1 doesn't work. So that leaves us with 3 options now. Position 2, position 3, or position 4. Agree? Position 4, okay. Let's erase position 2 and 3. Where would we draw the other one? Like this, right? Where do you want to draw that arrow? Like this? You want to draw it the other way? Okay, so draw it at the other end like this. Well, that's drawn front to front, so that's not going to work, right? Let's try the other way. Okay, that's drawn front to back, right? Front to back right there. But then the resultant vector is drawn from, that doesn't work, right? From the finish to the start. So position 4 doesn't work either. It's kind of funny that we had 4 positions and we're picking positions and we picked the 2 wrong ones first. But that's okay, because we're doing this for the first time, right? That's why we're teaching it, as opposed to why you're just being set free on questions without having been taught it. Position 4 doesn't work. So that means it's going to be position 2 or position 3. Either of these will work. Either of these will work. My suggestion for you, only because it's easier to find the angle, is to go position 3. Look at what we have now. We get an 85 kilometer per hour wind blowing to the east. We're aiming in this direction right here, somewhere north and west. We end up going straight north. Let's take a look at our vector diagram. Front to back, that works. The resultant vector is drawn from start to finish, that works. Whenever you get a question like this where you're drawing your dotted line vector first, please draw your wind or your river current or whatever so that it's front to front with your resultant vector. Draw that one first. That's the easiest way to do it. Okay? Draw it front to front with that resultant vector. Guys, even logically, right? We just take a step back from this for a second, from the physics of it, from the math of it, and go to the intuition of it. You want to drive directly north to Calgary. There's a wind blowing to the east. Where are you going to aim? Over here somewhere? If you want to go north and there's a wind to the east, don't aim to the east, because it's not going to take you north. If there's a wind to the east and you want to go north, then you're going to have to aim kind of to the west, right? To kind of counter that wind. Does that make sense? You have trouble drawing the diagram? Think of it like that. Think of it like that. Picture yourself driving your car and say, okay, I'm going to have to aim kind of north and west to compensate for that wind, right? Draw your vector up there. Okay, and it should kind of fall into place. All right, not too crazy math-wise, but understand that this time I'm not solving for my resultant. I have my resultant, 500. But I am solving for my hypotenuse. So the math is still the same, even though I'm solving for a different variable. We're going to call this not R, because it's not R. The dotted line is R. Let's call it V, velocity. Call it C for the hypotenuse, right? A squared plus B squared is C squared. Call it H for the hypotenuse. It doesn't really matter what you call it, right? Call it roly-poly-oly? Sure. Sure. You might want to have a symbol for that because it might get a little bit awkward writing that out, but 85 squared plus 500 squared still gives me the hypotenuse. This side of the room is going to solve for that. And theta is the inverse tan function of 85 over 500, opposite over adjacent. This side of the room is going to solve for the angle there. 5.1 times 10 to the 2 is our speed, and then our angle is going to be 5.7 degrees, 9.7 degrees, and that would be, what's that going to be? We're going north and we're going east. Hey, wait a second. Looks like it's west, right? North and west. Look, the angle is not towards the east, right? It's on the west side of north. So is it going to be west of north or is it going to be north of west? West of north, north of west. Actually, from the north, right? West of north. 9.7 degrees west of north. How'd you draw it the other way with the 85 down in position 2? Then you would have gotten an angle of 80.3 degrees or 80 degrees, but it would have been north of west. Same thing. You feel comfortable with that? Kind of the same thing, largely the same thing as we've been doing over the last day or so, but a little bit trickier, I think, because we had to draw that dotted line vector first. And although mathematically that doesn't make it harder, graphically, conceptually, it does make it a little bit harder. All right. Yep. Yeah, go ahead. I'd like you to take a look right now, please, at questions 6 and 7 on your worksheet. Taking a look at question number 6, we'll set it up here at the very least. It says the captain of a ship wants to go directly south. Wants to go directly south. Colleen, if the captain of the ship wants to go south, is that a solid or a dotted line vector? That's a dotted line vector, right? So let's draw a dotted line vector to the south. We'll assume that the ship actually goes where we want it to go. So it's going to the south at 15 meters per second. But there's a river current of 5 meters per second to the east. That's a solid line vector. Where do I draw that solid line vector? Remember when you've got a river current and a dotted line, the solid and the dotted line, you want those two to be front to front. So let's draw that over here. My other vector, my third vector, is right there. Let's relabel that 15 so it doesn't get mixed up there. That goes with the dotted line. This is the solid line is the one that I'm looking for. And the angle is right there. So remember where you want to go, dotted line, and then that dotted line vector has to be drawn front to front with some other vector. You guys can do the math on that one now. Let's draw the diagram for number 7 as well while we have it here. The pilot of an airplane wants to go directly south at 130 meters per second. Solid or dotted? Solid or dotted? He wants to go south. He actually goes south. It's going to be a dotted line to the south at 130 kilometers per hour. There's a wind blowing to the west at 20 meters per second. That's solid because that contributes to where he actually goes or where he wants to go. Where are we going to draw that? Right here? Sometimes what I find is that when people are drawing these diagrams, okay, they forget, and that's okay. We all forget things. But what's a little bit tougher to accept is that people don't think about it. Okay, you draw it like this, okay, because you forget how to draw it. That's fine. Right, Colleen? So let's think about it, though. Where do we have to aim? Well, if we want to go south, but there's a wind to the west, are we going to aim southwest? No, we're going to aim over here somewhere, right? If we want to aim over there somewhere, then clearly I've drawn that 20 meters per second in the wrong place. So let's draw it over here. Even if we forget that 20 meters per second should be drawn front to front with the dotted line vector, we know it's got to be over there somewhere because we know intuitively, ballpark at least, where we've got to aim. Right? We've got to aim down and to the right, south and east. All right, mathematically, again, you can solve for that. Solving for the hypotenuse there. Got it? Yes? Okay, I'm going to allow you to keep working on this if you're still working. And I'm going to allow you to move on and try questions 8 and 9 as well if you're finished these questions, okay? We're not going to spend a great deal more time working on these here today. What you don't finish in the next probably 5 minutes or so, we'll just leave you with homework for tonight, okay? Tonight. All right, have a look up here, guys. We want to take a look at number 8, at least part of it. It says the captain of a ship wants to go directly north at a speed of 35 meters per second. Wants to go. That's a dotted line, right? That's where the ship goes. Okay, where does the ship go? Where it wants to go. So it's directly north as a dotted line, 35 meters per second. Now, there's a current to the east. We don't know what the value of that current is. We don't know how fast that current's moving, but we know that it's to the east. Remember, the current is a solid line vector, and that solid line vector has to be head-to-head with the dotted line vector. We don't know what that speed is. That's what we're going to try to find. Where are we going to aim? We're going to aim up this way. That makes sense, right? If we want to go north, but there's a current to the east, then we better aim kind of north and west, not north and east. Now, what are we aiming at? Well, it says the speed of the boat without the current would be 50 meters per second. That's like looking in the back of that magazine on the airplane, saying the airspeed of this plane is 830 kilometers per hour. That's how fast it can travel without wind. That's how fast the airplane can aim towards Calgary or Edmonton or wherever it's going. So we're saying here the speed of the boat without the current would be 50. That's the speed at which the boat can aim. That's going to be that solid line vector that's up into the west. Now, what are we looking for in this case? Speed of the current, right? Speed of the current. Now, just like all your other questions, this is a Pythagorean theorem once it gets down to math. It's a Pythagorean theorem question. But usually you've been solving for the hypotenuse. This time we're solving for one of the sides. So instead of being a squared plus b squared equals c squared, solve for c, this time it's a squared plus b squared equals c squared, solve for a. So a ends up being equal to not the square root of b squared plus c squared, but rather c squared minus b squared. 50 squared minus 35 squared. Does that make sense? You don't need to find an angle here, right? Okay, you're not asked to find an angle. You're asked for the speed of the current. We know which way the current goes already. We're told the current goes to the east. So find an angle here. Maybe you can find an angle right here, the speed at which you aim. That would be okay. But you're not asked for anything about the aiming, right? You're asked for the speed of the current. All right, you guys feel okay with that? Okay, I'm going to leave you with number 9 to draw the diagram yourself for number 9 and solve it mathematically with number 9. We'll take a look at it tomorrow, make sure you're okay with it, and then maybe we'll quiz you on it on Monday or something like that.